the time, I would like to give some introduction about IESA and what we are doing and how are we working in the industry and things like that. So my name is Vishwanath. I work as a director, workforce development in the organization called IESA, Indian Electronic Semiconductor Association. This is basically we are into 20th year of operations, and we it's a premium industrial body for ESDM and electrical electronics, and we have a fantastic set of 450 plus members who are already into electrical electronics manufacturing, supply chain, and all kinds of. No, if you talk about design companies or packaging companies or no supplying companies, everybody is our member, and we directly work with Ministry of Electronics and IT, MIT, and also with all the state governments. Our core area of activity is working with central government in terms of helping them to design the policies as per the industry requirement, and also with the state government, we help them in all these aspects actually, right? So as an industrial body, we are happy to run this webinar for students benefit on a monthly basis. Every month once we do it. We call a fantastic no speaker, industry specialist who is well versed veteran in the industry, and much now. I know I just don't want to further delay. I just would like to invite the speaker for the session for today's session, Mr. Shivakumar. And I just wanted to take a couple of minutes to introduce Mr. Shivkumar, sir. He is basically a person who has got 25 plus years of experience in the industry. And he is basically a person who has created a very big, what do you say, in the dent in the uh, training the students, final year students, and the finishing school concept. His organization, Mavin Silicon, he is the founder and CEO, and he has been trained around 1 lakh plus students to get into the industry. And today, his technical seminar will help you to understand more how to get into the industry as well as how to shape up your career for a future. This will be a fantastic session for you guys, wherein you can take all your notes and then make a note. And I have a lot of faculty members also join. And if they have any queries also, in the end of the session, we can have a Q&A, or you can just type a Q&A session. You can type your questions and Shivkumar sir will take it, right? No, I just don't want to delay further. I would like to welcome Mr. Shivakumar onto the stage. Shivkumar sir, you can now start your session, sir.
Thank you, Vishwa. Thank you. Can you see my screen? Please confirm. And
Yes. It is visible, sir.
Thank you. I'm making settings. Is it changing?
Yes, it is.
Okay, good. Thank you, Vishwa. Good evening, everyone. I want to take this opportunity to thank IESA, Vishwanath, and the entire IESA team for this great opportunity. I want to take this opportunity to share my experience, how my journey has been in semiconductors. So the topic is how young engineers like you can build your long-term career in the semiconductor industry. So to build your career, you need to understand our history, how we started our journey long back. Without knowing his history, you might not be able to decide whether chip design is your cup of coffee. That's the first question you should ask yourself. You don't really need to choose VLSI, very large scale integration, because it looks fancy, or you want to boast yourself to your friends that you are dealing with chip design. Definitely, you should not choose chip design just for that sake. You must be inspired by what we have done in our journey. Today, the biggest challenge we face with young engineers is lack of knowledge. Many people don't know the history. So history is important. Let's understand how we built this industry, how we started. Our journey started with chip makers like Texas Instruments, Intel, great engineers like Jack Kilby, Maurice Chan, Bob Noyce, Gordon Moore. They all created chip design and fabrication. Different people contributed to different things. So you look at our journey, actually we started our journey with making chips for calculators. In 1960, that was our dream. We wanted to create calculator. Today, calculator is nothing. Nobody uses calculator because calculator itself has become an app. You can download calculator, or calculator could be the default app on your smartphone, and you can do everything, right? But our journey started off with calculator. And then companies like Intel, they wanted to make chips for personal computers. And then companies like Apple, they wanted to make system on a chip, complex chips for smartphones. Steve Jobs introduced smartphone at Apple. It was very popular. And then we wanted to automate everything as much as possible. So IoT, Internet of Things, became popular. Today, you look at the way you book cab, the way you order your food through mobile apps. Everything is happening through connected devices. It falls under IoT, Internet of Things, or it could be Internet of Everything. And now what's happening is we are moving towards AI, artificial intelligence. This journey is going to continue. We will be making more and more chips for new technologies like AI, artificial intelligence. So we started our journey with simple devices like calculators, and then PCs became popular. Then later on, Apple introduced smartphones. Smartphone became popular. And today, we are making more chips for IoT, connected devices, and artificial intelligence. When I say AI, it's obvious we all want to use Chat GPT. And to run Chat GPT, we need advanced data center, advanced infrastructure. For that, we need to make more and more customized AI chips. How are we achieving all these things? Through innovation. We have been so innovative. For example, you look at the processors. We started our journey with x86 processor. Engineers call it as CISC, complex instruction set computer. And then ARM introduced a RISC processor, reduced instruction set computer, primarily for IoT, Internet of Things, and smartphones. Today, most of the smartphones use ARM processor. And then NVIDIA's GPU, primarily for computer graphics. video games. They never thought that their GPU would be so popular for artificial intelligence. GPU has got parallel architecture, and that works fine for AI applications. So today, NVIDIA is at the top in semiconductors. Everyone wants NVIDIA's AI chip. Have we stopped there with NVIDIA's GPU? Not really. RISC-V has become popular. You consider Intel's x86 or ARM's processor or NVIDIA's GPU. In our journey, everything has been proprietary. But engineers want open source. How about having something very similar to Linux operating system? Linux is based on open source kernel. So you can download the kernel and customize as you prefer. That's why Linux is very popular, a Linux operating system. So we also wanted to create something very similar to this for chip design. So we invented a processor called RISC-V. It's an open ISA. I will talk more about it little later. So there has been so much of innovation. Processor has been changing. CISC to RISC, RISC to GPU, GPU to RISC-V. This is what you need to know. Then how are we continuing our journey in semiconductors? How we create new chips, new processors, the same way we also need to upgrade the fabrication process. So our journey started with older technology nodes like 180 nanometer, and then it has been changing 130. And then today, you look at the mature nodes, 65 nanometer, 45 nanometer, and then advanced nodes could be 5 nanometer, 2 nanometer, and then we are moving towards 1.6 beyond. This is possible because of EDA. Without electronic design automation, we can't create complex chips using higher technology nodes. How we used to design chips long back, right? It might not work now. We used to do everything manually, but today we have to design chip with the help of EDA, electronic design automation. So the important thing that I want to communicate is we have been so innovative. The industry will do something new. We will always do something new. And this is going to be very interesting for young engineers like you. So you may ask me the question like how things are changing. What is really happening in the semiconductors? We are using the latest processor like ARM's RISC processor or NVIDIA's GPU or RISC-V. CISC is outdated. We might not be using CISC in the future. Everything will be based on RISC, reduced instruction set computer. That itself is a huge thing in semiconductors. The same way, we are also upgrading the fabrication process. Today, we are dealing with higher technology nodes like 5 nanometer, 2 nanometer. Everything is based on EUV lithography. We are also looking at different methodologies like chiplets, 2.5D, 3D packaging. We might not be able to change the transistor technology beyond certain limit. For example, we have been using CMOS, right? And then we have come up with gate-around transistor, GAA, FET, and then CFET. But beyond certain point, we might not be able to create new technology. So we need to look at how to live with maybe 2 nanometer or 1.6 nanometer and then do more. If you want to do more, then you need to look at how to design chips differently. That's where chiplets are becoming popular or packaging becomes popular. So that could be another thing, how everything is changing in semiconductors. One thing that I want to highlight here is there are major transformations happening in semiconductors. 2025 to 2035, I would say next 10 years, it's going to be our game. Whether we would be able to do something great with AI, artificial intelligence, that depends on chip design. How are we going to create new chips? So everything is changing in semiconductors. Let's look at what is really changing. Why the world is talking about semiconductors. You might be hearing the news here and there, right? United States, why US is prioritizing chip fabrication, why it's something important, what's happening between United States and China, what's happening between China and India, and who is going to win the game, who is going to be the world's powerful country. That depends on semiconductors. So let's look at the transformations. When we started our journey, it used to be like mostly chip makers used to make chips and they used to sell chips. This is the important thing you need to understand. Still, companies like Texas Instruments, what they do, they make chips, they sell chips. Intel, it makes processors, it sells silicon. So you need to identify the product developer, someone like OEM, original equipment manufacturer. Is there anyone who is making laptop so that I can sell my chip? That's what Intel does. And that is traditional way of doing semiconductor business. It's changing now. Today, you look at most of the product developers, companies like Apple, software companies, companies like Meta, Amazon, Microsoft, they all make their own chips. So no more, it's going to be like only Intel, Texas Instruments, Infineon. They are all chip makers, but beyond chip makers, every OEM and software company would also be making their own chips. Why are they doing it? They are software company. Amazon is providing cloud access for Prime Video. They just need to buy server. They have to build data center. So why Amazon has to make chip? That's how Amazon wants to differentiate its service from Netflix. Amazon is competing with Netflix. Look at this possibility. So you have Prime Video, you have Netflix. Which one is going to win the race? It depends on semiconductors. So Amazon is making its own chip to differentiate its services. Similarly, Microsoft is making its own chip, whether it's with OpenAI or Microsoft. ChatGPT needs customized AI chip. So Microsoft prioritizes chip design. Apple, why everyone loves iPhone? Because Apple makes its own chip, system on a chip, A series chip. So that's a huge shift in the future. Almost everyone, all kinds of product companies, all kinds of software companies will be making their own chips, primarily to differentiate their products and services. Chip design is the only way how these bigger companies can differentiate their services and products. And the entire world is looking at balancing global semiconductor supply chain. Everything is coming from Taiwan. You want to make advanced chip, it has to happen in Taiwan. And Taiwan is very close to China. And that's the concern for United States. So that becomes a geopolitical situation. Now, US wants to create foundries. Foundries are happening everywhere in the United States. They want to make chips in their own country. That's called balancing global semiconductor supply chain. So India is also prioritizing it. So every country is prioritizing the semiconductor ecosystem. So every country wants to have a good semiconductor manufacturing ecosystem. That's the ultimate goal. The entire world is looking at how to balance the global semiconductor supply chain. Then the third one could be the impact of AI, artificial intelligence, how AI is transforming the way we design the chip, how AI is transforming the way we fabricate the chip. That's a huge transformation. That's what today I'm going to discuss with you. So let's look at why the world is prioritizing chip design. Why semiconductors? Look at here. In our life, we deal with various electronic devices. We use smartphone, we use PC, we use tablet. When we go to office, we might use monitors, smart TVs, smartphones. And you might also use equipment like treadmill, static bike in gym or fitness club, right? So you look at your life schedule. For example, you wake up in the morning. To wake up, you might use your smartphone. You set the alarm, and that's how you wake up. And then you want to do some workout, probably you want to play some music. You can connect your smartphone with speaker, and then you can play music. So your life almost depends on smartphone. For example, you look at the center here for emails, calls, WhatsApp, Gmeet, LinkedIn, Twitter, Glassdoor, to book cabs, Uber or Ola, or Google Maps, Google Pay, Paytm, all kinds of apps. That's what you might be doing with smartphone. More than 80%, you do everything through smartphone. Smartphone is important, right? At the same time, you also need different devices. For example, you go to office, right? Then at office, mostly you will be using laptop. You might want to run simulation, or you might want to edit some document, or you might want to use projector to do some presentation. You need Wi-Fi access, right? So the way you live at office could be different. And then you go to gym, maybe when you go back home, you have some treadmills, you have a static bike. They also need chip. So here you look at, I highlight these devices in different color. Can you see? Devices in brown, for example, smartphone, PCs, tablets, smart TV. All these devices, they are OS based, operating system based. So they need complex SOCs. At the same time, equipment like microwave oven, coffee machine, projector, or treadmills, static bike, AC, refrigerator, washing machine, dishwasher, they might use microcontrollers. We call them as embedded microcontrollers. This is the fundamental you should understand. We don't make all devices the same way. We have different approaches, primarily two approaches. We use embedded microcontrollers for real-time systems, and we use complex system on a chip for OS-based application. They are totally different. Let's look at what is embedded systems. When I say embedded microcontrollers, they are specialized computer designed for a specific application. So it's for one particular application. You think of your laptop, you have multiple applications like Microsoft Office, browser, video applications. You can play video games. So you have thousands of applications. You can run multiple applications in parallel. When you want to run multiple applications in parallel, obviously you need operating system. So how it happens, you have the application, you have the operating system, and then the operating system is the one that manages all these applications. And they are not real-time systems. What you see might not be real-time. So what do you do on your laptop? That's not real-time. Applications like ABS on car, sports watch, they are all real-time systems. You need quick response. So there, we are not looking at running multiple applications. So it will be like customized application. And mostly it's going to be like one simple application running directly on the chip. So we call this as bare metal software. Bare metal software means whatever the application you run, the application directly runs on the hardware. It doesn't need operating system, period. Typically, embedded microcontrollers would be simple. In some cases, it could be complex also. Most of the embedded microcontrollers use ARM's Cortex-M, very popular processor. And it will have some cache, power management unit, debug unit. There will be on-chip memory like flash and SRAM. So to interface with SRAM and flash, you need controllers, and you might need some customized accelerator, depends on the embedded application. And it will provide interfaces so that you can connect the external devices with your chip. The best example is your smartwatch. It's based on embedded microcontroller. But we don't make laptops the same way. So to realize laptops, nowadays, everyone prefers system on a chip. So Apple introduced MacBook M series chips. You would have heard about M series chips. They have M1 series, M2 series, M3 series. So it's a complex chip. Almost it does everything for the MacBook. So it has necessary processors. So you can run the operating system directly on the chip. It doesn't mean that there will be one M series chip and then everything happens through only one chip. Of course, there will be other chips also. The board is going to be complex. I will also throw some light how basically we build any product. But what I want you to understand is we make laptops using complex chips. And that's completely different from the way we create applications like smartwatch or coffee machine or microwave oven. So coffee machine, microwave oven, static bike, and dishwasher, washing machine, they all based on embedded microcontroller. So, excuse me. Embedded microcontroller doesn't use any operating system. But when it comes to laptops, servers, they all use operating system. Now let's take a look how Apple is differentiating its smartphone. Apple is using A series chip for iPhone. The journey started with A4, and then today we are talking about A17, A18, A19. The current chip is based on higher technology nodes like 3 nanometer. You see the difference between A4 and A17. A4 was based on 45 nanometer technology and the frequency was 1 gigahertz. But today we are talking about A17. beyond A17, A18. And it demands 20 billion transistors. So to pack 20 billion transistors, we need 3 nanometer technology, and the frequency is very high. Because the chip is complex, it has to process so much, including AI applications. So look at the motherboard of iPhone 16. Here you can see the details. iPhone 16 is based on A18 processor. Can you see here? So this is the chip. This is the main chip. Everything is going to happen through A18. Doesn't mean that everything happens only with A18. Of course, iPhone demands multiple chips. On the board, you can see other chips as well. So Apple makes its own chip, A18, and A18 is fabricated using technology called 3 nanometer. And this SoC, system on a chip, uses the processor ARM. ARM is well proven in the smartphone market. I would say ARM is a silicon proven ISA, instruction set architecture. So without having any question, you can choose ARM processor for any kind of IoT and smartphone application. And that's how ARM is going to dominate next 10 years. And here you can see some more details, right? So this A series chip demands more than 20 billion transistors, right? It's very complex. To pack billions of transistors, we need higher technology node. And the chip is fabricated by TSMC. The chip is designed by Apple. So do you really need only higher technology node to realize smartphone? Not necessary. To realize chips like A18, you need higher technology node, but of course you need other chips like modem chips, flash driver, power controllers. We can see various chips provided by various vendors. Apple also buys all these specialized chips from various vendors, and you can see the technology node differences. So we use different technology nodes for different chips. How we classify technology nodes? We classify technology nodes like 180 nanometer, 250 nanometer, older technology nodes. Still, we use older technology nodes for industrial controls or telecom equipment where size doesn't matter, but we want to create chips. 40 nanometer, 65 nanometer, 90 nanometer, we call them as mature technology nodes. This is the hot cake. Most of the applications use mature technology nodes, well proven. When I say mature, well proven. Automotive, computing, data storage, wireless communication, power management, all these applications use chips based on 40 nanometer, 65 nanometer, and 90 nanometer. And that's what's going to happen in India. Whatever the foundries we are setting up, basically we are looking at these applications, and there are huge requirements. All these product companies, automotive product companies, cloud server companies that make cloud servers, companies deal with computing, companies deal with wireless communication. They all want chips in bulk, chips in bulk. So in India, we want to produce chips in bulk. And that's how the manufacturing plant can be profitable, right? So they need chips in bulk. At the same time, companies like Apple wants to make A series chips, M series chips. That's completely based on higher technology nodes like 3 nanometer and beyond 3 nanometer, 2 nanometer, right? But there will be demand for both higher technology nodes, mature technology nodes, and older technology nodes. So the important thing is complex electronic devices like smartphones. For example, iPhone 16, you look at, it demands multiple chips. Just with one chip like A18, you can't do everything. Even Apple itself buys various specialized chips from various companies like Texas Instruments, NXP, Infineon, Broadcom. You can see all the names. Texas Instruments primarily, right? It's highly specialized in analog. Now, what's happening in the design space? Let's look at. Most of the companies want to create system on a chip. And that's how basically we can optimize power performance area. Now you look at the M series chips. They demand various processors like CPUs, GPUs, accelerators, image processors, DSPs, digital signal processors, security and neural engine, power management processor. That's how they build this kind of complex SoC. And you think of smartphone, you will be running different applications, and different applications demand different processors. Otherwise, you can't optimize performance, you can't optimize power performance area. We always need to think about it. So we need customized processors, dedicated processors for different kinds of applications. But here the complexity is different processors will be based on different ISAs, instruction set architecture. And when you choose any processor, CPU or GPU, you also need to understand the software. How are you going to support the software programmer? So you need to provide him the implementation framework, how the software stack will be built. So processor will always come along with software stack. And that's a big challenge. If you're going to deal with multiple processor vendors, then different vendors will have different licensing scheme. And then you need to work with their software tool chain. So life is going to be difficult, right? So why do I need to deal with multiple processors? That's where RISC-V community under RISC-V International introduced an open ISA. So here you look at, to create any kind of chip, we can go with one processor. So using RISC-V, we can think of creating all kinds of processors like CPUs, GPUs, digital signal processors, image processor, accelerators, neural engine, whatever you want to create. You should be able to create everything. That's how we are looking at, that's how the future is going to be. I'm not saying that today you can do everything, it does the magic, but RISC-V is going to evolve further and further, and that's going to become very powerful like Linux operating system. How you do various things with Linux. Linux is very powerful because you have multiple flavors of Linux, Ubuntu, Red Hat, and hundreds of flavors. So tomorrow you want to create your own processor, no issues. You can download the specification, go to RISC-V International, download the specification, you can create your own processor, no restriction, because it's like Linux, open source. But when it comes to instruction set architecture, we don't say open source, it's a specification. So we call this as open ISA. I'm trying to correct you. You are not supposed to talk casually like RISC-V is a open source processor. Don't say that. RISC-V is an open ISA, instruction set architecture. But in the processor world, we deal with general purpose ISAs, specialized ISAs, right? So for example, IBM is well known, IBM 360, it's popular for more than 50 years, Intel's x86, it's continuing for more than 40 years. ARM is continuing for more than 35 years, and RISC-V is continuing for more than 10 years, and that's going to continue. That might not happen with custom processors. We call them as special purpose ISAs. So RISC-V will emerge as an industry standard ISA for all computing devices. This is the one point I would like to highlight. You look at this complex SoC, you can think of creating almost all kinds of processors. I'm talking about only processors. What do you find at the core? Of course, the chip needs other components like system controller, a wireless IPs, memory controllers, memories, interfaces like USB, right? But the most complex part is how we create the engine, how we build the engine for the chip. The engine would be composed of various processors. So that is where RISC-V is going to be more powerful in the future. Now let's take a look, semiconductor supply chain. At this point of time, semiconductor manufacturing doesn't happen in one place. It's distributed across various countries. So global network of companies produce trillions of chips at nanometer scale. So how this supply chain has been built, semiconductor supply chain. Look at here. So various countries are popular for various things. Let's look at Apple's iPhone. How Apple makes iPhone. Let's look at this example. Apple is based out of United States. We call Apple as OEM, original equipment manufacturer. They also designed their own chip. So they have A series chip for smartphone. We are talking about iPhone 16. So in this case, A18 is the chip. So Apple has headquarters in United States. So their designers create the architecture for A18. We are talking about A18. So the design happens in the United States. So US is very popular for owning a lot of patents, chip design, design expertise. They are highly specialized in design architecture. And you get almost all kinds of IPs from United States. Now, to create this A18 processor or SoC, system on a chip, let's be very specific, A18 is a system on a chip. Apple buys a processor from a company called ARM, ARM. ARM is based out of UK. So ARM is a fabless IP company. They don't sell silicon, they sell only processor as an IP. So Apple buys ARM processor and integrates the processor as part of the chip. Also, Apple might buy IPs from various IP vendors, primarily from EDA companies like Cadence. And then Apple might outsource the implementation work to countries like India and Israel. Apple may have operations, or Apple may outsource some of the project work to services companies. So India is well known for design services. So what we do is actually we work for companies like Apple, maybe directly or indirectly. So we are well known for workforce. You look at India, approximately more than 20% of world's chip design workforce is in India. So more than 1 lakh engineers working on VLSI and embedded systems. So we are very popular for chip design expertise. We deal with IPs, chips, and SoCs. We are very well known for design verification and physical design in India. So Apple might outsource verification work. Hey, you verify my chip, you implement my chip. So that's what happens in India. That might happen in countries like Israel. But eventually, Apple will do everything. It creates the design, and then it simulates, and then it takes the design through design flow, physical design, and then finally they create GDS2. GDS2 is the final outcome, the netlist. It's called routed netlist. And Apple doesn't fabricate the chip. This is what you need to understand. Apple is a product company. They design the chip, they outsource the fabrication to a foundry in Taiwan. Can you see? Taiwan is very small. India is bigger than Taiwan. So we need to work closely with Taiwan to learn how to manufacture the chip. That's what I dream about. And Taiwan, there is a popular foundry called TSMC. You can see at the bottom. TSMC makes world's advanced chips, right? So you look at Taiwan. Taiwan is very popular for fabrication. And Taiwan produces 41% of all processor chips and more than 90% of advanced chips. Everything is almost coming from Taiwan. You consider advanced chips. So A18 is based on advanced technology node like 3 nanometer, and that could be possible only with foundry like TSMC. So the fabrication happens in Taiwan. Okay, now the chip is there, A18. Then Apple designs the motherboard in the United States. It also buys chips from various vendors or companies like Texas Instruments, Infineon, NXP, ST Micro, various companies. They all provide specialized chips. Companies like Broadcom or Qualcomm. Qualcomm is highly specialized in wireless communication. And Apple might use EDA tools again from Cadence or Synopsys or Siemens, right? So Apple designs the motherboard in the United States, and then it might outsource the PCB work to countries like China. So Apple may have its own plant in China, and then the PCB work happens pretty much in countries like China. China is well known for PCB design, printed circuit board. That's how Apple makes motherboard in China. And once the motherboard comes out with all chips, then in China, they have planned to create the smartphone with peripherals like display units, all the stuff they have to assemble together. And that's how iPhone happens in China. And what's happening in China now, it's replicated in India, especially the product assembly, not the PCB, at least product assembly is going to happen in India. I will talk about it a little later, right? Now, we are talking about PCB for the iPhone. So the iPhone comes out. Now you consider the fabrication. Let's look at how TSMC fabricates Apple's chip. To fabricate the chip, TSMC will buy some chemicals, materials, machines. For example, Netherlands is very popular for EUV lithography machine. Companies like ASML based out of Netherlands. So TSMC gets the machine for their plant from Netherlands. So Netherlands contributes in terms of EUV machines. At the same time, Taiwan will procure all kinds of materials like wafers, gases, other kinds of machines might come from Japan, right? So this is how different countries contribute to semiconductors. This is how you can visualize how Apple makes iPhone. So United States is popular for chip design, and countries like India is popular for design services, and Taiwan is very popular for fabrication. China is very popular for product assembly, and Malaysia is very popular for OSATs, outsourced semiconductor assembly and testing, and that's what's happening in India now, right? So you look at the chip production stages. As I mentioned, initially everything starts with design, and then it goes through fabrication, and then product assembly, then testing, packaging. So the chip is going through all these stages: design, fabrication, then assembly, then testing and packaging. So overall, the market size is 2000 billion plus electronic system market, and semiconductor market size is more than 600 billion, and foundry could be more than 150 billion, embedded software could be 20 billion plus, and ED and IP could be 15 billion plus, right? So we have different segments. And the current revenue of semiconductors is more than 600 billion, and that's going to grow further. So we are looking at becoming a $1 trillion industry by 2030. And today, in terms of market capital, NVIDIA is at the top. But overall, you look at the ecosystem, we have design ecosystem, we have the ecosystem of chip makers, and then we have the manufacturing ecosystem. So what you see in the left-hand side, pretty much design ecosystem. I can simplify this. Chip makers, or we call them as IDM, integrated device manufacturers. So here, these companies could be fabless or IDMs. When I say IDM, mostly they sell silicon. For example, companies like AMD, companies like NVIDIA, they are all fabless chip maker. So they work with the external foundry like TSMC, and that's how they make silicon, okay? Companies like Intel, companies like Samsung, here you look at Intel and Samsung, they have their own foundry, so we call them as IDMs. But overall, they are all chip makers. They make chip, they may have their own foundry, or they may outsource fabrication to external foundry. All right. Now, all these chip makers need three things: IPs, electronic design automation, and engineers like you. So when I say IP, they need different kinds of processors, memories, interfaces. All these IPs primarily come from fabless IP companies like ARM, RISC-V, Rambus, all these companies. And they also get IPs from EDA companies like Cadence and Synopsys, right? And for the chip design, they also need brilliant engineers like you. India is well known for design services, so there are bigger companies like Capgemini, Accenture, Wipro. Wipro is one of the best services companies. It's there for long, right? So this is a big opportunity. You want to build your career, probably you might want to look at companies like Wipro, Capgemini, L&T Technology Services. They hire engineers in bulk. They hire thousands of engineers. Also, all these IP companies, EDA companies, companies like Cadence, companies like ARM, they hire top talented engineers, but they might not hire engineers in bulk. They might hire hundreds of engineers every year. So you have plenty of opportunities, especially in India. And what's happening in India, it doesn't happen in the United States because US is popular for design work, but India is well known for implementation work. So implementation demands engineers in bulk. We need an army of engineers, like thousands of engineers. So that's a huge advantage. And also you can be part of chip makers. You want to build your career, either you can work in fabless IP company or EDA or design services, or you can directly go to chip makers like Intel, NVIDIA, AMD. companies like Qualcomm, Broadcom, NXP, Continental, Analog Devices. Analog Devices, one of the best companies in my experience, right? And Samsung, we can deal with mobile SoCs at Samsung, right? And of course, all these software companies like Amazon, Microsoft, they are also creating their own chips. So they need engineers, but they might not hire engineers in bulk. I'm not trying to color it like you go to any company, they need thousands of engineers. I'm not saying that. Design services companies need engineers in bulk, but most of the other companies need brilliant engineers. Of course, everyone struggles to get enough engineers, is the point. And today, Maven Silicon is working closely with the chip design ecosystem, right? And we are also coming up with IC manufacturing codes to support the manufacturing ecosystem. Now you look at manufacturing ecosystem, Tata is coming up. Tata is setting up foundries, and there are companies like Micron, they are setting up ATMP facility. So there will be more activities related to manufacturing. They also need engineers, but again, they don't need engineers in bulk, right? Now, what's happening in India? India's semiconductor market is approximately 50 billion plus today, and that's going to grow up to 100 to 110 billion by 2030. So the market is huge, and the government has approved more projects worth of more than 20 billion USD. So you can see various projects that are happening in India, how Tata is setting up fab, OSATs, and companies like Micron setting up ATMP, Keynes, Semicon is setting up ATMP facilities, OSATs, and various fabs. So all these things are happening. Of course, you need to understand how AI, artificial intelligence, is changing the way we do business in semiconductors. AI demands advanced data centers. So we have to create new kinds of processors like TPUs, tensor processors, NPUs, GPUs. The same CPU will not work for artificial intelligence. For example, Google is introducing TPUs. So we need to look at how to support the language models, large language models. They all need specialized chips like TPUs, NPUs, AI chips. So to create all these chips, we would also be looking at using higher technology nodes. Obviously, we need 3 nanometer, 2 nanometer. We also need new methodologies like 2.5D, 3D packaging, chiplets. That's how we would be able to pack more and more stuff. And then we would be able to create powerful AI chips. Of course, EDA will use AI for their tools. So everything is going to be AI-driven EDA. For example, you look at all these EDA companies, right? Siemens or Cadence or Synopsys, they are all looking at how to use AI, artificial intelligence, effectively everywhere. I will throw some light how it is going to change. So the AI is going to grow massive. It will be used everywhere, like transportation, education, commercial, healthcare, everywhere AI will be used. But the important thing is the evolution of AI will change the way we design chip. For example, you look at chip design, the code reviews, how we do linting, or how we design chips using agents. That's going to be completely different. You consider chip verification. We want to automate the test case generation. We want to automate the coverage closure, verification sign off. We want to improve the efficiency of verification sign off. And similarly, EDA, you look at, EDA will also try to optimize these services, right? So design services companies will also be using new methodologies. And machine learning in EDA is going to be very powerful. And that's going to be useful for things like test case automation, code reviews. And similarly, AI will be used for physical design. Physical design will be completed with higher efficiency, I would say higher efficiency only with AI. And chip fabrication, silicon testing, PCB testing, everywhere AI will be used efficiently. So that is there. AI will increase the efficiency of chip design. AI will increase the efficiency of chip manufacturing. AI will increase the efficiency of testing. All right, that's obvious. But what would be the major benefit of AI? Applications like ChatGPT will demand specialized chips like AI accelerators. That's a huge market. That's a huge market. So currently we are creating more chips for smartphones, laptops, but beyond smartphones, laptops, even IoT applications, right? The industry would be looking at creating more chips for AI, artificial intelligence. That's our future. Today, you look at most of the bigger companies like NVIDIA, Google, Intel, they are leading the AI accelerators market with their next generation AI accelerators. So here you can see the roadmap. They are all coming up with their new chips, NVIDIA, AMD, Intel, Google, Amazon, Microsoft, Meta, Broadcom. Here you look at, it's the mix of chip makers and software companies. That's the beauty. So everyone, almost everyone is going to make chips for AI, and everyone is participating in the AI race, right? So that's going to be very good for semiconductors. But overall, you look at VLSI, very large scale integration. AI chips have huge demand, and applications like IoT, smartphone, tablet, home automation, automotive, especially self-driven, they all demand more and more chips. The fast growing markets would be home automation, high performance computing, robotics, security, electric vehicles, 5G, and the new trendsetters would be artificial intelligence, autonomous, quantum computing, digital supply networks. You might want to consider the new trends, how the future is going to be. So you have great future in semiconductors. We have seen the ecosystem. You can be part of fabless IP. You can be part of chip makers. You can be part of EDA companies, and you can be part of design services companies. We have seen the list of companies. So you have plenty of opportunities. I want you to remember design services companies hire engineers in bulk, and other companies like fabless IP and chip makers, they need top talented engineers. Of course, they don't hire engineers in bulk, right? So the difference could be like 100 engineers, typically 100 engineers every year for fabless IP company. So every IP company or EDA company or chip making company you look at, they might hire 100 engineers per year. But you look at services company, they might hire 500 engineers per year. It depends on, again, the market situation, right? So I'm not defining it as a golden standard, but you have plenty of opportunities in India. In addition to design, you can also look at the manufacturing ecosystem. There are new fabs, OSATs, ATMP facilities, and then all these chip makers, they also want to deal with packaging like 2.5D, 3D packaging, chiplets. 2.5D, 3D chiplets, again, they need more and more engineers like you. Of course, fabrication is a different domain, but there also you can explore different kinds of opportunities. How AI is going to replace human? I want you to remember this: AI will not replace us. When I say it will not replace us, what it means is we have to be really smart, right? So AI will not replace subject matter experts. So now you really want to compete with AI, then you have to have system level understanding. System level design expertise is critical. For example, as a young engineer, you need to know what Apple does, how Apple makes iPhone, or how it makes A series chips, M series chips, good knowledge. Of course, you don't really need to understand how it makes PCB or the entire system, but you need to have a good knowledge at high level. Today, whatever we have seen, that kind of knowledge is required. But on top of it, fundamentally, how we deal with systems, what we mean by embedded microcontroller, what we mean by OS-based SoCs, and knowing one good processor is fundamental, is really, really required. For example, knowing RISC-V is going to be very, very useful for your career. So you start your career with processor. Please listen carefully. You can't start your career with knowing one processor. RISC-V is a very good option. And then we are setting up good manufacturing ecosystem. There will be plenty of opportunities. So the future is going to be more like we would be dealing with high quality work, high quality work. So AI will take care of mundane things like writing same kind of test cases, writing thousands of test cases, running simulation multiple times. All those things will be taken care by artificial intelligence. But still, we need brilliant engineers who can monitor the processor, who can guide the AI, who can customize the AI application, right? So we need hundreds, thousands of brilliant engineers like you. So my quote here is, look at here, this is my quote: let's design AI chips. So we all want to deal with design. We want to deal with creative work. That's what it means. Let's design AI chips and let AI implement its AI chips. When it comes to verifying the chip, when it comes to implementing the chip, let's use AI effectively, artificial intelligence effectively. That's what it means. Thank you. Questions, please.
Uh, Thank you so much, Shivkumar sir. It was really wonderful. It was really wonderful from the basics. I'm sure the guys who are till now attending, I think there are 50 students who came and passed by, but the students who are currently available would have got a fantastic no overview on how to start their career in semiconductor as a industry and how to build their career also. And there is only one question as of now, it is posted. What is the future of civil engineers in semiconductor field? Probably that's the only question as of now it is posted. Maybe you can just handle it. And further, if any queries are there, please post it in Q&A and sir will be able to handle it. Please type it in Q&A. We just wanted to answer it through Q&A no session. Thank you, Kumar sir. Please,
No,
maybe you
no,
wanted to answer for this civil engineering students how to get into semiconductor field.
right. Uh, we prefer electrical and electronics engineers. Of course, you can also deal with chip design, no restriction, but you need to be very good at electronics basics. But again, there could be challenges when it comes to starting your career. People prefer electrical engineers, electronics engineers. So there you have to convince them. So it's going to be difficult initially, but you can do that. But apart from electrical and electronics, computer science engineers can also do chip design, and mechanical engineers can deal with manufacturing, chip manufacturing. So there are opportunities for mechanical engineers, computer science engineers, civil engineering. There could be some challenges, but again, it depends on the interest. You can be an odd man out in the market, right? So you can disprove me, you can disprove anyone if you are truly passionate about chip design. But you asked me this question, to be safe, what I would say, we prefer electrical, electronics, computer science engineers, primarily. Any other questions, please feel free. Okay, let me read.
Yeah, there are another 3, 4 questions, sir. You
Okay.
can just go through.
So it's a good question related to technology node. So one question is, with the shift toward 1.8 nanometer and 2 nanometer nodes, we are hitting the physical limits of silicon. How would companies like NVIDIA and AMD would balance the push for smaller transistors versus investing in advanced packaging like 2.5D, 3D ICs to keep Moore's law alive? See, 1.8 nanometer and 2 nanometer, the world is moving towards 1.6. But again, it depends on the innovation in transistor, right? So currently we use FinFET, and beyond FinFET, GAAs, gate around FETs will be used. And then vertical stacking would be the other option, CFET, that could be other options, right? So fundamentally, it depends on the transistor innovation is one thing, right? Beyond silicon also, we need to think there could be different options like how we can use quantum computing. That's the future beyond silicon. But as of now, you look at the technology node limits, we have to come up with a new transistor technology like FinFET, GAAs, and further, what can be done. We have to prove the new transistor technology beyond GAA, what could be possible, right? We need to prove this. Otherwise, it's going to be difficult. But we can't simply take back seat. So that's where packaging options are really needed, 2.5D, 3D, and chiplets, right? Even chiplets. And that's how we would be able to pack more and more components onto a single chip. And that's how we can follow Moore's law. We can make sure that Moore's law is going to be alive, right? So that's my answer. If you're a student from ECE branch, what will be your roadmap? What kind of skill you will learn? With respect to chip design, what I can say, I will learn processor. I tell you, you talk to anyone like me, I will ask you this question. How do you classify systems? Is the fundamental question. I can give you an example. You have smartwatch, you have laptop, you have Amazon server. How do you define them? So smartwatch is based on bare metal embedded microcontroller. A laptop is based on system on a chip. It demands operating system. And then cloud server is based on hypervisor. So you need to know the difference. What is bare metal embedded microcontroller? What is OS-based SoC? And what is hypervisor? Only engineer can talk like this. If you know at least the terminologies like what is microcontroller, what is system on a chip, what is hypervisor, that convinces me. Now to understand all these things like embedded microcontroller or system on a chip or hypervisor, you need to fundamentally understand the processor. RISC-V is a very good option. Open ISA, you can download the specification. You can actually you can visit SWAYAM Plus, IIT Madras. I have published free courses. Okay, it's completely free. Go and learn RISC-V, and it explains various layers, how we deal with hardware design, how we deal with software stack. And that should be the roadmap. So no more stories like I know digital electronics, I know multiplexer, I know flip-flop, I know latch. That's again the problem. How many engineers know all these fundamentals very well? But beyond fundamentals, today what is really needed is you need to understand systems. Practical knowledge is required, right? And that's how you can build your roadmap. You start off with processor, understand processor, and using processor, you can understand pretty much everything, the software stack, and how we design processor itself. There you have to use digital electronics, pretty much pipeline design, right? Explore various things, and then try to run a simple embedded software onto the processor that you create, and that will create a solid foundation. Of course, in that process, you need to learn some HDLs like Verilog, VHDL, and you will be dealing with EDA, right? So that's how you build your expertise. But you start with something small. Don't look for something complex, right? Someone comes and says like, why don't you create a complex memory controller? Forget about system on a chip, right? Don't buy all these things. Don't go behind protocols. You know, people will throw or terminologies like you should know AHB, you should know APB, you should know AX. Start off with processor, explore digital electronics, implement the processor, write your own C code, run the C code on the processor, understand the entire flow, and you be a solid guy for chip design. All right, let me see. I'm not able to. Okay. One second. It's difficult to. Okay. Some drone chip design, I will come back. I want to answer to straightforward questions. Okay, very good. How important is a master's degree versus industry skills for core semiconductors roles? See, master degree, we also offer executive MTech for working professional, right? So my goal is different. If you are a UG undergraduate student, then the expectation will be very clear. The industry will expect you to know the fundamentals very well. Subjects like digital electronics, if you know HDL very well, you know CMOS fundamentals, and you have implemented some good projects, right? That might work in your campus, but when you come out of your campus, then you might want to understand more to compete with more engineers, right? So there you would be looking at adding more keywords into your CV. Then you might want to learn more or go to places like Maven Silicon and learn more, add more projects. That could be another approach, right? But there is nothing like mandatory. You must have master's degree. But if the master degree is very effective, there you can learn the systems, for example, how to design an SoC using a processor like RISC-V or ARM, and how we deal with different systems, and then knowing software and hardware, pretty much everything. See, when you go with master's degree, you will have advantage at the same time. You have to convince, you have to prove yourself. If you don't prove your expertise, then you will not be considered as a PG. So it's a double-edged sword, right? So you have to be careful, but doing masters with premier institutes, I would say, is an added advantage. Institutes like IITs, BITS Pilani, they all offer masters. Uh, I'm talking about GATE score-based uh, postgraduate programs. That's very powerful, no doubt, because you learn something very solid from post-graduation. So post-graduation makes you specialized, right? For example, you are an electronics engineer, you can choose either embedded systems or VLSI, or you can go with software development also. But when you become a postgraduate, for example, you do masters in VLSI, then you are good for chip design, right? You don't really need to deal with embedded systems. Of course, you can choose embedded systems and do, but you don't really need to deal with software. Look at the possibilities, right? So the possibilities could be very limited, either chip design or embedded systems. Everyone is in need of engineers. Probably you might get job in software industry, but no hard and fast rule, right? So you can start your career as you prefer. So you have 1 year internship with the NXP. Then now what to do? You have to apply for the job and fine tune your skills. What you have done at NXP matters. See, one thing is when you do internship, okay, you apply for a job, you should be able to tell the interviewer what you have done. It doesn't have to be something like high-end work. At NXP, probably you would have written some script, you would have dealt with some automation, but can you explain that properly? And definitely, whether you have done internship or whether you have worked somewhere else, every interviewer would be interested in your fundamentals, how you understand chip design, and basics like digital electronics, and whatever you claim as part of your work experience. Let's say you claim that you know system Verilog. Probably you would have uh, run some system Verilog test cases, but you don't know actually how we create test cases in system Verilog. Then that's going to be a problem, right? So you sit back and understand the language, understand the methodology. Do you really know system Verilog? Do you really know UVM? And how are you going to convince, right? So you have to refer your resume as a golden reference, and don't try to claim too much. That's my suggestion, right? Make it precise, and whatever you claim, you should be able to convince, prove. And how can the academic institutions help create the semiconductor workforce required in India? Collaborate with IESA. I would say, if you're from a college, you are a professor, please talk to Mr. Vishwanath. There are many experts. They are well connected with the industry experts. They can provide all kinds of support. They can guide you, like how you can partner with companies like Maven Silicon or anyone else, right? So they know who is doing what, and our expertise, and who is good for what. So I would say, as an academic institute, you must work closely with IESA, attend their forums, educate yourself. IESA Vision Summit is happening in Feb, and you would be able to interface with many experts, right? So that will be more effective. So educate yourself. You will come to know what's happening in semiconductors, and work closely with Mr. Vishwanath, and he can guide you further. All right.
So thank you so much, sir. Thank you so much, Mr. Shukumar,
No
sir,
problem.
for your 1 hour 15 minutes of your valuable time. I know the value of your time. Participants, I would like to give a small announcement, like Shukumar sir was talking about. We have a yearly once a mega event happening called Vision Summit 2026, happening between 25th and 26th of February in Bangalore. Kindly, guys, no, visit our website, go through the informations. You guys can meet all different companies there. It is just your choice to come, no, meet up with them and build your career even from there, right? So thank you so much for all the participants. And no, I think we have given a right inputs to all the students for them to take it forward. Any more informations, you can reach out to us. You have our mail IDs, you can reach out to us. Thank you so much. Thank you, sir. We'll close the session. Thank
Thank
you so
you.
much.
Thanks,
Bye.
Vishwa. Thank you so much. Bye.